Good morning, everyone. Welcome to e-learning day number one. This is going to be a little bit different, isn't it? But we're going to do our best here. I still encourage you to open the notes from Canvas and follow along if you possibly can. I also encourage you as we do our learning this way. I'll be working through all of the examples in the notes, but as we work through the first couple, after the first one or two, I really encourage you to use that pause button and try and work the examples yourself before you watch me do it. That way, it's most like the classroom situation. Okay, we're going to go right in here and talk about expressing functions as power series today, uh, and we're going to reintroduce that term power series for you here. First, remember we introduced this term when we were building our Taylor polynomials in the last unit. What those Taylor polynomials really are just a shortened version of an infinite power series, where it's you want to think of it as just an infinitely long polynomial, and we still have the term center of the polynomial indicated by the term x minus a to the k, and the center would be a, and each power of x minus a has its own coefficient, c sub k. And we saw in the last unit when we were building these as Taylor polynomials, we had a special way to compute these coefficients if we were building a polynomial based on a certain function. Here we're going to go back and just look at general cases here. Uh, so those coefficients will be defined for you. And what we're going to be looking at today is noticing that uh, in these long polynomials, if you were to replace the value of x with a particular number, this power series becomes a series of constants. And we could then use our convergence tests to decide if this power series converges or not. And what you're going to find is that is going to be a sometimes. Depending on the value of x you pick, this will be a series that will converge based on one of our convergence tests. And depending on other values of x, the series will diverge. And so we end up with what's called an interval of convergence. That interval is always centered around the center of the polynomial. And so we use some of the terms that are synonymous with circles, in that a circle has a center and it has a radius. And so in this context here, you will find that all the values of x for which the power series converges is all centered around the center of the polynomial a, and that gives you what's called a radius of convergence. In other words, there will be some number for which, if the values of x lie within that distance of the center point, kind of like on a circle when you're a certain distance from the center, uh, the series will converge. And if a value of x lies outside of that distance, the series will diverge. And if you put the radius, if you take the center point and move one radius distance to the right or left, we then get an interval of convergence. So for example, our center point might be 1 and the radius might be 2, and then the interval would be anything from -1 to 3. Let's look at an example of a power series that kind of comes from familiar territory first, and we'll talk, and we can see the term radius and interval at play here. Here's a, you might remember from a couple of weeks ago, we one of the types of series you're supposed to know really well is the geometric series. Here's a good example of one where the ratio is r, and the first term is the number 1. And so the series would generally go like this: 1 times r, 1 times r squared, and on. And we know that a geometric series converges if the ratio is between -1 and 1, or we could also say that the absolute value of the ratio is less than 1. And when it is, we also learn what that geometric series sum is, and we know that it's the first term divided by the quantity 1 minus the ratio. And so what this equation is telling us here is this particular geometric series expressed in this way has a sum 1 over 1 minus r, provided that the ratio is less than 1. Now today I want you to observe it. If we just simply replace the r with an x, you could see it as something we would call a power series, where we have every power of x from 0 on, making the first term a 1, and we could see it also, but we want to see it as a geometric series. And so if the x value is between -1 and 1, then the geometric series will converge. But what I want you to think of it as today is thinking of it as in this way. On the left side, we have an infinitely long polynomial. And on the right, we have another function of x, 1 over 1 minus x. And so what this is saying is this power series, if x is chosen to be a number between -1 and 1, if we were to sum all of this together, it would be the same as evaluating the function 1 over 1 minus x. And so in this context here, as we introduce the term radius and interval, what we're going to say here is that this power series has a radius of convergence of 1, because if any value of x is within 1 unit of 0, the series converges. And I'm going to just make a note of that here. Now we almost always will denote here the absolute value using absolute value notation. We're saying that any number within 1 unit of 0 is going to give you a convergent series. I should have said that the radius is 1. And so if I were to expand that out, the interval of convergence is any number between -1 and 1. I brought my graphing utility along with me here so we can demonstrate this principle, and you can see the interval of convergence working here. So what I've got is the black graph is the graph of the function 1 over 1 minus x. And in the red is the beginning of our power series. Now, we would have called this the first degree Taylor polynomial in the last unit. But as I slide the n up here, now this is centered at 0. Now you guys notice that the red graph is now sticking very close to the function 1 over 1 minus x, but only when the x values are between -1 and +1. That's indicating the interval of convergence there. And if I slide this n even further up, it doesn't seem to be affected by that. The graphs only seem to coincide on the interval -1 to 1, indicating that's also an indicator of the interval of convergence. So any value of x within 1 unit of 0 will eventually converge to the series will converge to the function. Otherwise, it's not going to. It's going to diverge. Well, that was an introduction to the term radius and interval, kind of what they mean. We're gonna make a new video where we look at some examples where we give you a power series and we make it and use the convergence test to determine the radius and interval of convergence. We'll see you at the next video.